So good evening. Thanks for having me. Today I'm going to talk about reinforcement learning. Fernando and myself, Fernando is a colleague in the MTech. In September 2018, we made a 4-hour reinforcement learning course. And obviously we don't have 4 hours today, we have 50 minutes. So I'm going to try and condense all of that into kind of a quick summary and kind of so you understand the basic concepts within reinforcement learning. So, but before we get there, let's just talk a bit about what we're trying to do as the MTech. We're a remote team of researchers. We're very multidisciplinary. We have PhDs, master's students, engineers, data scientists, etc. And we kind of began with survey publications. We began with a survey on a year in computer vision. We covered 14 different subfields within computer vision, for example, classification, object detection. And then we moved to another survey in multimodal methods, which is mixing computer vision and natural language processing. So we kind of have two projects, two visions and two projects and two long-running blog series which attempt to fulfill these visions. Number one, we want to model and distill knowledge within AI. So that's what our survey publications aim to do and what we continue to do with our blogs and future discussions, as well as this talk right now. I'm trying to distill knowledge within AI. And then our second goal is kind of like trying to build AGI, or just more kind of put nicely, make some progress on making intelligent machines. So you can check us out on our website, on Medium, and on Twitter. So let's get started. So yeah, part one is about the introduction to reinforcement learning. There is no deep learning in this part. And we're going to cover applications, inspirations, visions, and then the core concepts of reinforcement learning. I really want to go through the core concepts and not go too far into the advanced techniques, because all of the techniques are at the root of it pretty similar. We'll cover some model-based approaches, GridWorlds, and kind of model-free approaches, and a few environments. If we have, I don't think we'll have time to cover a lot of part two, but if I have time, we'll cover a bit of value function approximation and a few other things. And don't worry if you find anything confusing or you didn't get anything. All the slides are online, and I'm going to share them after. And this talk is also being recorded. Cool. So this is my disclaimer slide. There's a lot of math, a lot of algorithms, and a lot of terminology in reinforcement learning. As you can see here, we have policy, value-based, model-based, model-free, and here we have policy optimization, dynamic programming. So many terms, it's almost kind of, you can kind of get lost in the terms and kind of be just confused. But if there's anything I want you to take from this talk is that all these methods are kind of doing something very similar at the core. They're trying to optimize reward. They're trying to optimize an agent's reward throughout its lifetime. No matter the technique, all of them try to do this same thing. No matter the terminology or class we can put these algorithms into, they all try to optimize a reward. The same way a dog would learn from you giving it treats. If it doesn't do the trick, you don't give it treats. If it does do the trick, it gets treats, and it learns to connect the actions it does to getting the treat. And that's why after many treats, it learns how to do the trick. So let's get into the applications. So in 1992, there was a TD Gammon, which bet all the experts in backgammon. That was a kind of a big moment for reinforcement learning. TD stands for temporal difference, one of the biggest methods in reinforcement learning. And then I'm sure we're all aware of 2016 AlphaGo. This is Lisa Dahl playing AlphaGo, and the referee has to come over to him at some point to tell him that he's lost. This was kind of like a watershed moment in AI because not many people saw it coming so soon. Some people thought Go mastery is 20 years away, but it came out of nowhere with these reinforcement learning algorithms. And then since 2016, we had AlphaGo 0. So the key difference between AlphaGo 0 and AlphaGo is that AlphaGo began by doing imitation learning. It tried to imitate humans, which is kind of like a supervised learning technique. given a board state, do the right action, act like a human would. The difference with AlphaGo 0 was that there was no human inputted data. It learned completely by itself what a good game of Go is. And then since then, Alpha 0, they got rid of the Go, and now it's good at chess, shogi, Othello, and maybe any zero-sum board game. So that's board games. There's also 2D video games, which you can represent by an array of pixels. Here we have the arcade learning environment from Atari from the 60s, 70s, 80s, not the 80s. And here's a large-scale curiosity when there wasn't actually an extrinsic reward for that environment. It learned purely from its own curiosity. It made its own reward function. And the funny thing about this is that it found death in the game boring. Because if death happens, you just go back to the start. That's boring. So it learned to kind of continually surprise itself. It learned to act so that it was surprised about the future. So that's arcade games, 2D games. We can also have 3D robotics and simulations. Here we have DeepMind in 2017, where they learned locomotion. We have spider-like creatures jumping over chasms. We also have humanoids coming up, jumping over obstacles. And we don't teach it how it should move. We just give it reward. That's the clear part here. We don't tell it that this is how a humanoid should run. We just tell it to go forward. You get more reward by going forward. Here's one example. Yeah, so very impressive. OpenAI and also in 2017 also had quite a similar approach, but this time they used self-play, where two agents equally matched would play against each other. And because they're equally matched, they learn how to become better and better. And here we have a goalie versus a footballer, or you shall not pass, where the goal is just to get past the other person, the other agent. And again, we don't teach them how to do it. We just tell them what's good if they do it. So, for example, a good reward there would be to get past the opponent. So that's simulated 3D robotics, but we can actually apply this to real robotics. The issue is that real time is kind of slow compared to the simulation. So here we have arm for arms. Google has tens and tens of these robots trying to grasp very difficult objects. We find it very easy to pick up any object, but robots find it very difficult. Picking up eggs, picking up toys, they're all slightly different in how you should grasp the object. So some people say that this is the upcoming industrial revolution, when robots are not just stuck in factories. They're going to be able to handle dynamic environments like your home or other buildings. So then, but that's not just what ORL can do. There's also world models in 2018 by Schmidhuber and David Hack. Here's the actual simulation of the race car, where you press left and right to go around the track. But the simulation on the left is the simulation within the agent's head. It's built a good model of the future. Such a good model of the future within its own head that it's able to dream possible futures and then use these futures to then play well in the real world, which is the simulation. So it didn't even need the real simulation. It could just learn in its own simulation and then transfer it to the actual simulation and do well at that. So that's world model, predicting the future. There's also language grounding, the task-oriented natural language grounding, where the goal of the agent is to go to the green pillar, go to the short pillar, go to the green short object, go to the red short pillar, etc. And the agent is given the input pixels and this instruction, and eventually, after 40 hours on lots of GPUs and lots of CPUs, the agent will learn maybe what green means. Debatable, but it learns that green is not blue. And in this sense, it's grounded itself in what maybe some words mean. It could learn go to is different than run away from. So that's natural language grounding. And currently, we're trying to do some fundamental work in of our own in research. This is our own repo. You can go here and start if you want. We're applying an agent to do the same, but in household environments, where the goal is to pick up cups or other objects. So you can check out our work. We're actually going to release a blog next week on that, and we're jokingly calling it From Cups to Consciousness. So keep an eye on that. So DeepMind in 2018, Quake 3. This is a very complicated game, but the superhuman levels. This is also unexpected. I didn't see this coming. I thought this was 2022, but no, it was 2018. These agents learn to collaborate and compete. Collaborate with other agents and compete against real humans, professional humans, and they won. And if we actually analyze the internal state of the agent, we see that it's learned to represent certain concepts. For example, I have the flag, I'm at the enemy's base, I'm at my own base. And the great thing is it can also play with human teammates. These agents are so robust that they can play across different levels and play with human teammates. And there's a lot of cool technology like mass population training, fast and slow timescale, or enhance. So I've kind of given a flash through a lot of applications there. There are a lot of games, a lot of robotics, a lot of 3D robotics. But what is this field really at the end of the day? It's the intersection of many different fields, and it's come about over the last 60 years. For example, the intersection of engineering, mathematics, and computer science is optimal control. And since we've had robots, we've always wanted to find the right way to control these robots in factories or elsewhere. Another big inspiration is psychology. For example, Pavlov's dogs, or classical conditioning, or dopamine, even from neuroscience. Dopamine is how us humans or other animals are motivated to do anything. When we eat pizza or any of this, all of this kind of releases dopamine within our head. So in a sense, we're reward-seeking animals. So, but at the end of the day, these agents want to act best in the world, and we can define what best means. So let's get into the core concepts of reinforcement learning. If there's anything I want you to get from this talk regarding all the maths, you should understand these core concepts at the end, so that when you read a paper on reinforcement learning, or even your job is automated by reinforcement learning, you should kind of understand what automated it. So yeah, the formulation. It's quite simple. You have the agent and you have the world, and it's a loop. It's the agent environment loop. The agent makes an action, AT here, and gives it to the world, and the world will come back with XT and RT, which is the state and the reward. Did it complete the task? If the goal was to pick up cups, the reward might be high. If it's not picking up cups, the reward will be low. And the state, we'll come to that later, but that's its representation. That's the agent's representation of what he sees. And this loop repeats on and on and on, and that's reinforcement learning. So in more formal terms, reinforcement learning is the field of sequential decision-making under uncertainty. That's the important part, because we don't know what the future holds. You know some of your actions can affect the future, but you're not sure. And there's a lot of uncertainty with every part of the world. And then what the goal is for this agent is to maximize long-term cumulative reward for the agent. So let's focus on a few of these terms. Long-term, you might want to eat ice cream all day, but you might feel bad the next day. So that's not really maximizing long-term reward. You want to maximize long-term reward over your whole lifetime. Cumulative, in that sense, you might be happy about something that happened 10 years ago. You might be proud of something, going to college, doing well in that exam. That's, in that sense, it has accumulated. Your reward has accumulated over your whole life. And maybe you could say after, on your deathbed, you might say, I've lived a good life. I think I've maybe tried my best to optimize cumulative reward. And quite simply, it's learning how to act. We want to map states to decisions, situations to decisions. And I keep applying these analogies to real life because I think it often applies. Real ORL is like real life. But this is not a self-help talk, so here's something concrete. Here is the environment agent loop in 12 lines of code. Here we import Gym, which is a library for holding many different environments and reinforcement learning. And we make the carpole environment, but it doesn't matter which environment we make, it's the same 12 lines of code. We run 20 episodes, we reset the episode at the start of every episode, that makes sense. You might travel 1,000 miles, but at the end of the episode, you want to go back to where you began. And then we set 100 steps in the environment. We can choose to render the environment, print the observation, which is what the agent sees. And here's the two most important lines. Here we take a random action. That's what that dot sample here means. So if there's two actions, left and right, flip a coin. You can go left or right. It's a completely random agent. And once we have this action, we then feed it to the environment. And then the environment will return to us the new observation. If I turn left, the world looks different. The reward, whether I'm completing the task, and whether the episode is done. That's important. If the goal was to pick up 1 cup, that done would be true if I picked up the cup in the last action, if the last action was pick up. And if it's done, then we can restart again and begin. And that's reinforcement learning in a nutshell. So the real complexity here that I showed you in all the terminology and all the math and all the algorithms, the real complexity is choosing the actions. What actions to choose to maximize reward. So let's talk a bit about state. Here we have a mouse, and there's cheese in the bottom left corner, and the goal of the mouse is to get to the cheese. That's where the mouse will get reward. So the state is the representation of what the agent sees. So here it could be a single number, saying if there's 3 times 3, so 6 times 6, 36 states. It could be just a number from 1 to 36. Or it could be an XY tuple, the X and Y coordinate of the mouse. Or any number of states. You can make the state. It's up to you. And often we kind of group a sequence of states and transitions into episodes. And they usually end in a terminal state. You might go into lava and die. That's a terminal state. You might get the cheese. That's also a terminal state, but it's a good terminal state. Transitions are how we group state, action, reward, and then the next state, tuple. Cool, so you can have many different types of states. As I said, you can design it yourself. In the previous case, it was just XY tuple or an integer index of where you are in the world. Here we could have actual bounding boxes, we could have vision input, we could have images coming in. If it's a self-driving car, you might have 8 concurrent images coming in every 60 times a second, for example. And you can choose to represent the state however you want. So for example, if we only have the position of the car, of the red car, and we had to get across the road, it might not be good enough to know the position of the car to avoid collisions. You might want to have acceleration, velocity, the other car's positions. All of this would help you achieve the goal more. So that state, it seems pretty simple. There's also reward, as we talked about earlier. So it can be an arbitrary number. It can be minus 5.2x6 or a billion, or even 0 at each time step of the environment. But at the very last time step, you get a 1 or a -1. And that's, for example, chess and go. You're not getting reward for each step in the environment. You get reward if you win the game, draw the game, or lose the game. 1, 0, or -1. So, yeah, you can set up, it can be set by the environment, or it can be changed by the algorithm designer itself. And it's up to you. And it's, again, related to dopamine, which is reward-motivated behavior. And here's a kind of controversial statement. Can all goals be described by the maximization of expected cumulative reward? I haven't heard any counterexamples whenever this is asked, but you can think about that yourself in your own time, and maybe all goals can be described by this hypothesis. So we have reward. That's what we get at each time step of the environment. But what we really want to maximize is all the rewards, the cumulative reward, what I talked about earlier. And this is what we call the return, GT. We also discount it over time. So we care more about rewards now than in the future. You care more about ice cream now than ice cream in 10 years. You want ice cream right now. And because of this, we discount future rewards. So the value, gamma, can go from 0 to 1. If it's 1, you actually don't discount it. You're just adding all the rewards from time step t, gt, till the end of the episode. So if it's 0.99, that represents you care a little tiny bit less about the next reward than the current reward right now. So why we discount? There's many reasons why we discount. Well, number one, it's convenient mathematically. So for infinite episodes, after 500 steps, you don't care about things after 500 steps because it goes to 0.006. And just to be clear here, the gamma is powered to k. So gamma to the power of 0 is 1. That's what the first return is, or t plus 1. And then the second one is gamma to the power of 1, gamma to the power of 2, etc. So that's why on the 500th step, gamma is to the power of 500, and you'll be multiplying the reward you get on the 500th step by 0.006. And another reason we do this is just there's more uncertainty into the future. You care more about earning reward right now. And here's just a code example of how we could compute the returns. If we have the rewards, you do 20 actions, you get 20 states in return from the environment, you get 20 rewards. Once you have the rewards in a list, we can go through it backwards and calculate the return this way by accumulating the G. So we have what we're trying to optimize, but how can we get there? One way to do this is to calculate the value function. The value function is what it is what it says on the tin. We're trying to predict the value of being in a state, VSS. So what is the value of state S? And what it actually is doing is trying to calculate the expected return. Here we have this formula again, or t plus 1, gamma or t plus 2, gamma squared or t plus 3. We're trying to calculate the expected return of the future. We don't know the future, but we can calculate the expectations of the future. So here I can change all this RT and RT plus 2 into just GT. I'm trying to, yeah, as I said. There's also the Q action value function. Instead of just the value of the current state, we're trying to get the value of the current state and action. So not just how good is this state, how good is this state, and if I did this action and I went left, or if I went right to avoid the oncoming car. Obviously, in the second case, that's a better value because you're avoiding the oncoming car. And here again, we have expected, E stands for expected, return given the current state and given the current action. That's the value function, and this is what many, many reinforcement learning algorithms are trying to calculate. So now we're actually getting to the actions themselves. We have a value function. Could we get an action out of it? One way to do that, we have the policy. So the policy describes the map from situation to action. You can have a deterministic policy. So if you're in America, turn left. If you're in Ireland, turn right. Stupid example, but there's no stochasticity within deterministic policy. However, in the stochastic policy, you might have, regardless of where you are, 30% chance of turning left, 70% chance of turning right. We're representing all the actions by a probability distribution. And here's a nice kind of graphic. The agent's looking at a map. What should he do in each of the states? So policies, value functions, return, reward so far. Another big concept is the Markov assumption. And what it really means is that the probability of the next state, given the current state, is the same as the probability of the next state given all the previous states, your entire history. It is an assumption, but it's a very strong assumption that many ORL algorithms use. And what it means is that we can forget about the past and just focus on the present. What we need right now is just the present to make our best action. And that's the assumption. And all of this comes together, all the concepts I've just talked about, into the Markov decision process. MDPs for short. And it's formalized as the tuple of sets, S, A, P, or gamma. S and A, we covered, they're the state and action spaces. If you can only go left and right, the set of actions you can take is left and right. States might be all the states you can go into the world. P is the state transition probability distribution. So what this represents is the probability of getting to S prime, the next state. If I go left, will I ever get to America? 0% probability. I need to make more turns than that. That's what this represents. The reward function is if you're in state S and take action A and make it to state S prime, what is the reward for doing so? For example, if you pick up the cup and the goal was to pick up the cup, that reward function will return a high number. The discount factor we covered. And what the Markov decision process kind of intuitively says is that these states are, you see the whole world, but obviously this is not the case. I don't see what's in the next building. I don't know what's happening in America. That's why we have partially observable MDPs, short for POMDP. And this represents more what the agent sees rather than the entire state of the world. So that's almost the core concepts. Here, the model. Usually when we talk about model-based reinforcement learning, this is referring to the state transition probability matrix, P, and OR. If we had these, we could plan the future. If you knew what was going to happen for every action, you could plan thousands of time steps into the future, and you might be a billionaire by now. But the point is, we don't usually have the model. We don't know what's going to happen in the future, but we can approximate it. And here, obviously, this dog's model is bad because he's assuming that the treat is falling to the ground, but he doesn't know that it's a glass table. So dynamic programming needs access to the dynamics model. Makes sense. So that's the core concepts. And I'm happy to take a question or two there if anyone has any. Otherwise, I'm happy to move on. There's lots of things to go through. Yeah?
Yeah, so RL essentially works on processes which are kind of Markovian, or two processes which are Markovian, but then you have a whole lot of other problems which are not Markovian. Or is there any way?
So there's many variants on the Markov decision process. As I said, there's POMDPs. There's also relational DPs. I think the POMDP is a good example of not needing to know the past, because for example, you could use an LSTM, which represents the history of everything it's seen within it. So the agent learns how to deal with the past. Obviously, the past is useful in certain cases. So I think that's a good example. Go.
Yeah, just when you were talking on the P1, I do know that then the leaf state makes the Markov decision test. So it represents as a Bayesian model.
Yeah.
Then you say the probability of everything, and then it becomes a Markov decision process, and you work from there. Of course, it's representing those probabilities in a reasonable manner is kind of where the trouble comes, but in theory you can just convert it to a Markov.
Yeah, exactly. So how to represent the future and how to predict the probability of whether Trump will get elected or not, or any examples like these. Cool. So let's get to actually how these methods try to use the MDP formulation and maximize reward. So one way of doing this is model-based reinforcement learning. So you can either know the model or try to approximate it. In chess, we know the model. We know that if you move the knight here or the rook here, we know that's going to happen, and you can predict hundreds of steps into the future. But usually we don't know the model. I don't know what's going to happen in the future. So we have to approximate it. Here's a good example. The reward might be to get higher, but your model might not know that falling off cliffs is bad for you. So it really depends on how good your model is of the world if you want to maximize reward with model-based reinforcement learning. So it can be biased. And a big equation, one of the biggest equations in reinforcement learning that you should know is the Bellman equation. So I'm moving here. So the Bellman equation is how we decompose the value function into the immediate reward and the future reward. And how we do this mathematically is we put in our GT here, which is the return. It's our expected return for being in state S for the value. We unpack it into its RT plus 1, RT plus 2, and then we try to pack in the RT plus 2 part, take out the gamma, and we have GT plus 1. And because it's GT plus 1, a bit of extra maths, the law of total expectations, we take the GT plus 1, and that turns into the value ST plus 1. And now we've decomposed the value function into the immediate reward. Right now, what reward can you get? Plus the value from the next state. So this is a very important algorithm that's used in TD methods, it's used in dynamic programming, and it's really good to go over and over again. But at the end of the day, it's just immediate reward and the value from the next state. So how do we actually use this? But before that, you can do the same for Q. And so Q is the action value function, the value for doing an action and being in state S. So we can decompose that as well. V and Q. So a lot of methods use V, Q. They're the value functions. Okay. So how policy evaluation works is if we could evaluate any policy, it could be a random policy, for example, left or right, 50-50 chance. We can evaluate this policy to see how well it'll do in any environment. So how we do this is we can represent the current state, the actions we could take, and the future states we get to from doing those actions in a tree. And once we have it in a tree like this, we can then use the Bellman equation to work out what is the new updated value of the current state. And we do this by calculating iteratively, updating the value of S. So we actually multiply the probabilities of each action by the immediate reward you get, as well as the value of the future states you can get to. So what we're actually doing is just we're calculating the expectation of the future value you can get from if you were doing random actions, depending on the probabilities. I might have forgot to say that pi is how we represent policy. Pi is the map from state to action. So maybe it'll be more clear in an example. If in this environment, you can go up, down, left, and right, you get -1 reward for making an action in every step, except in the green squares. That's the terminal states. That's where we want to get to. What we do with policy evaluation and using the Bellman equation is we initialize all the values to 0. So 16 states are set to 0. And then we can calculate the new value for each of the 16 states by using the Bellman equation that I showed you here. We use the reward, the immediate reward, which is -1. Since if you move anywhere, it's -1, except in the green square, which stay at 0. And since all the values are 0, we multiply 0.25 by 0 for the 4 actions. And that's why we get -1 everywhere for the first iteration of this policy evaluation. What we're just trying to do is work out what is the value of each of these states for a random policy. 25% chance of going up, left, down, or right. And And if you keep repeating this, this is proven to converge. If you keep repeating this, you'll get more updated values. And as you can see, value 2, this in the second iteration, we see that the states right beside the green squares have a bit more value than all the other states. And this intuitively makes sense. You're close to the green state, which is where we want to go. So therefore, it's a good value to be close to the green square. And you just repeatedly apply this formula on all 16 states, again and again and again. And eventually it will converge. And the important part is that's just evaluating the random policy. We don't want the random policy, that wouldn't be optimal to get to the green state. And here's where policy iteration comes in. Once we have the value at any one of these steps, 1, 2, or 3, we can use that to act greedily. We know that being close to the green squares is better than being further away. And because it is, we can act greedily, which is taking the action which will which we think is the best value in the next step. So here you can see the arrows, and as they get updated, at the top it's completely random. If we update the policy after the value has been after the policy has been evaluated, then we can get a new policy by acting according to the value function. And as you see, the bottom policy in the bottom right there is pretty good. Maybe it's almost even optimal if you started in a random place. So this general idea is using any policy evaluation algorithm to work out what is the value of this policy, and then using your new value that you calculated to then find a new policy. Since you know the values of the world, you know it's better to be in the Bahamas than in hell. So you might act accordingly in the Bahamas, and you might act or aim to go from hell to the Bahamas because the value is better there, your belief about the value. And again, it's this evaluation improvement, and this has been proven to, as in this case right here, you eventually get optimal. So these discrete worlds I talk about are called GridWorlds. We made our own called Grid Universe. You can check it out on GitHub. They're kind of very simple environments that you can test very complicated ORL algorithms on. You can make any variation you want. So for ours, we did a lot of different variations. We added levers, doors, fruit, lemons, melons, apples, and mazes. And you can set the goals to be to get to a specific state. That's what we made. But regardless of all the robotics and the simulated robotics and all this cool stuff and first-person shooter games, these environments are still very important because we can design complicated scenarios, avoid the lava, get to the goal, and try to train these things to be safe as well. They're perfect test beds for a lot of scenarios. And a really good example is Sokoban. Now the goal is to push these blocks to these areas. And it's very, very difficult for humans as well, because you can easily get stuck. If you push a block into a corner, you can't pull it out. You have to restart the level. And because of that, every action should be very carefully planned if you want these blocks to go to the right place. So DeepMind did it in 2017 using a model-based approach. They were able to predict the future of where the blocks were going, and using that, they could plan with the predictions of the future. And on the right is Vicarious in 2017 using schema networks and causality, and a lot of different methods here to best plan. As you see, it's very complicated. You have to go up and down and left, to go around, all the way around just to get there, and very complicated maneuvers and a lot of planning needed to actually solve these levels. So that's GridWorlds, reward, the formulation, the core concepts, and Sokoban. So the rest of the iceberg, the main concepts that are really, really important in reinforcement learning. Continuous action state space. So here we have the actual park-hole environment. It's like trying to balance a broom on your hand. Same kind of thing here. You can go left or right. They're discrete actions. However, the actual state that comes into the agent, what the agent sees, is these 4 values on the left. Part position, part velocity, the pole angle, which might be minus 41 or 41, and the pole velocity at the tip. And using these 4 values, can the agent pick the right discrete actions over the whole episode to keep the pole standing up as long as possible? And that's the cart pole environment. It's a very good sample environment. But it's important to point out that you could flip these scenarios. The discrete actions could become continuous. There's a continuous version of cart pole. And to a bit more intuition on that, pressing down on the throttle on a car, that would be a continuous action rather than just on or off. You might push a little bit or push a bit more. And the same with, you can have discrete state values. And one of the big dilemmas in reinforcement learning is exploration versus exploitation. You might every Friday go to your favorite restaurant and you don't want to risk going to another one. What if it's bad? But sometimes, what if you just tried Joe's Pizzeria around the corner and things might change? You might find that to be your favorite place from then on. You have to do a little bit of exploration and take a little bit of a risk to see if you could exploit more. And obviously, the right balance is key, because at some point, we have to understand how our actions affect the world. But to do that, we have to kind of mess around and in a trial and error approach, work out what works and what doesn't work. And at some point, then we have to exploit and actually aim to maximize cumulative reward. So credit assignment, another very tough problem. Here in Pong, if you hit the paddle, 30 frames later, it goes past the opponent's paddle. But what actions did you do that actually contributed to you getting that point? It's kind of a delayed reward. And actually finding what you did, what actions contributed to getting that reward is one of the fundamental challenges in ORL. But also just in science, we don't even know if milk is good for us or bad. We haven't assigned the credit of whether what gives us cancer or not. It's very hard to assign the credit. And that's why it's related to causality. What actually caused you to get the reward? I mentioned the delayed reward. You might only get the reward at the very end. So you can actually use reward shaping to kind of help the agent. You could have a reward that says if you're closer to the goal, give it more and more reward until it's right on top of the goal. But that requires a lot of engineering. For example, if I wanted to train an agent to get me beer from the fridge, I'd have to have a pressure plate in the fridge that would recognize when the beer is gone, and then it gets reward. So it can require a lot of engineering to design these rewards. And there's a lot of ways to solve this. This is OpenAI in 2017, hindsight experience for play. It learned from its past experience of bad behaviors to then do better behaviors in the future. And there's a thing called reward hacking. Here, the agent gets a reward for picking up these boosters, but that's not exactly what we wanted the agent to do. We wanted it to finish the race. And why would you finish the race when you can get reward from these boosters? That's what the agent's thinking. So we have to be very careful that these systems will do whatever they can to get reward, and it might not be exactly what you wanted. So we kind of covered the iceberg there, and then there's model-free approaches. We covered a bit of dynamic programming, where we look one step ahead to calculate the value recursively for each state. We can then use the prediction of the next value states to then keep updating the value at the current state. So that's dynamic programming using the Bellman equation. TD, temporal difference, is one of the most famous methods in reinforcement learning. It uses an estimate of an estimate to keep updating the value at the current state. You can learn after one step. You take one step and you see how your value changed compared to your value of the future. I'll get a bit more into that. There's also Monte Carlo, which has to go to the very end of the episode. It might be 1,000 steps. and you can work out the value at each step along the way. So, yeah. So quite simple. If we do 1,000 episodes, we can count how many times we got into each state. We can accumulate the total return from being in each state, and then we just find the average. We just find the average of being in the Bahamas compared to hell, and the average should be higher. And we can prove that this converges to the actual value of the policy if n goes to infinity, as we visit each single state infinite times. So again, we just go to the very terminal state. We need to wait till the episode ends before we can calculate the new value function. That's Monte Carlo. Temporal difference. It uses this bootstrap, which uses, you try to go towards the target of the immediate reward plus the future reward of being in the next state, and you take that away from your current value. Using this, we can update current states, VST, towards the target. They're both equal. They should both be equal, but they're not, because all your estimates are wrong. By going towards the target over many thousands of episodes, eventually your value becomes good. That's TD one step, but it can be extended to 2-step, 3-step, and eventually it turns into Monte Carlo if you keep extending it enough. There's a lot of kind of mix and match between these algorithms. Here's n step, and as you see, it goes to Monte Carlo if n is infinity. So that's quite a bit of maths, a bit of algorithms already. You have MC versus TD on many axes here. We have exhaustive search, which is classical AI. We just try to search through everything and find the best result. And there's many ways to compare these algorithms along these dimensions. There's also Q-learning, which uses a similar TD learning update, but we use the Q value instead of V. And Q-learning, if this is the tabulated version, if we have the value for each of the states and each action in each state, we can represent this in a table if it's discrete, and we can update Q towards the Q target. It's a very similar idea to TD. And as we'll see, DQN uses this, but with value function approximation. Cool. So to take a step back a bit, we have a lot of environments in OpenAI Gym, and as you saw, Cartpole and many others. You have Classic, Joko, Atari. There's also new environments called VizDoom, which uses Doom engine. And here's a competition in 2017 where they had 7 agents or 8 agents playing against each other in a death match. And the whole goal is to make the best agent who can kill the other agents as much as possible. That's VizDoom, and there's also DeepMind Lab, where the goal is to avoid the lemons and collect the apples. And there's a full engine you can use to create your own worlds, specify your own reward functions, and train whatever ORL algorithm you want to complete these goals. So it's a general framework for getting stuff done, for achieving the goal. And that's the power of it, I suppose. Okay. How much time do I have? So I really wanted to drill in the core concepts. But if we have time, I have, I'll do 5 minutes of a bit of part 2. I knew I wouldn't have much time for this, but I'll go to the 2 main algorithms, DQN and policy gradients. What we covered in part 1. Part 2, we're not going to have time to cover much of this, but policy gradients and DQN, try to quickly cover. So what value function approximation does, we can't represent everything in a table, especially if it's continuous. There's infinite real numbers, so we should approximate it. We should use, for example, a linear regression or a neural network to just predict what the value is using neural networks and backpropagation and usual techniques in deep learning. So, but the problem is, it's not your typical supervised learning problem, cat or dog, or hot dog or not. It's a highly dynamic, stochastic problem that changes as the agent gets better at what it does. So therefore, there's a lot of instability problems, and you need a lot of tricks and a lot of cool algorithms to actually deal with this. So to quickly fly through this, I won't have time to go through the details, but DQN revolutionized the field in 2013, and everyone kind of got into this field by applying value function approximation and deep learning combined. That's where the deep ORL comes from. And there was many different alternatives and extensions to DQN. Yeah, but here's what actually is done in DQN. It takes a bunch of convolutional layers and fully connected layers, and finally the output will be the value of the 18 actions in Atari. That's the Q function that it's predicting. The DQN network is predicting. So there's a lot of these variations, as I was saying. Here you can see noisy DQN, distributional DQN, dueling DQN, prioritized DQN, and DDQN, double DQN. A lot of DQNs, and all of them were combined in Rainbow DQN. And as you see, the results are amazing. Even after just 7 million frames, it's doing better than all the other ones, and it's a very, very strong algorithm. And here's actually, if you look at the, I'm going to share the code after and share the slides, and the link will be here for a really good code example within VizDoom environment. I'll fly through policy gradients, but the simple idea, instead of everything you saw previously, was estimating the value function. What if we just estimated, tried to directly find the right policy, to directly find the right actions, directly differentiate into the policy to find the best actions, rather than finding the value function, which we can then use to get the best actions. This directly will optimize doing the best actions. So there's a lot of math in this. You have to skip it. There's a car call example, just 100 lines, super simple. All the maths kind of comes down to this one equation, and you put that in one line of code, and 100 lines, and it learns car call in just a few minutes. There's these baselines and advantages, which use the Q and V values as well as the policy. And then we get to this formula called Actor-Critic, which has the actor, which is the policy network, which directly tries to do actions, and then the critic, which is your usual value network, tries to predict how good the value for being value is for being in state S. And this is the culmination. Just a few months ago, 1 month ago, DeepMind StarCraft came out of nowhere. Dan in the audience there, we had a bet. I was saying 2020. He said 2022. Fernando, who wrote these slides with me, said 2021. Out of nowhere, 2019, they're beating expert players in StarCraft. I did not see this coming for a while. It kind of came out of nowhere. And they have a lot of cool, kind of crazy technologies, and 16 TPUs, training for 14 days, stealth imitation learning, all sorts of crazy stuff. But this is the culmination of all the techniques. Other policy gradient methods, TRPO, PPO made it simpler, better, and now everyone's using this. And here's PPO in action. Here's the Atlas robot simulated, and a humanoid who has to follow the ball. And to kind of summarize everything, PPO was applied to DotA as well, another real-time strategy game, and also beating 5v5 and 1v1 matches, using large LSTMs and a lot of computation to train these systems to become better than humans at these games. And they also applied it to robotics, where the goal was to point the right side of the cube towards the camera. And that's a very hard problem. We find it easy, but the agent has to learn how to use its actuators and vision systems to point the cube and manipulate the object. And to summarize why I showed these last two algorithms very fast, OpenAI had a big competition called Sonic Retro. They were testing generalization for algorithms in environments they hadn't seen, Sonic levels they hadn't seen before. And the top 3 places was PPO, Rainbow, and PPO. So this is really the state of the art in reinforcement learning at the moment. And we got back to the beginning. There's all these algorithms, all this terminology, and a lot of maths, but at the end of the day, all these algorithms are doing one thing. They're just trying to maximize or optimize cumulative return. Thank you. Any questions? I'll get the mic. Yeah, no problem.
Very interesting presentation, but beyond video games, like it seems like humanity's in a bit of a crisis, and maybe we need some higher intelligence, higher than our politicians, and we need a bit of fairness in the system and eradicate some corruption. And I'm just wondering, even just in terms of getting an AI to look at our resources like water or our economic systems, or could it come up with better solutions? Are we going to find ourselves, or our politicians, consulting an AI, looking for solutions and the best and fairest way to proceed in the allocation of resources or taxation policy or something?
Yeah, the short answer is yes. And I expected the question to come of more ORL applications. So I had this slide. I robbed the thing on the right. There's a lot of applications for actually optimizing energy. DeepMind actually had in one of their cooling centers in their data science centers, they learned to optimize it so they used less power, used it more efficiently. So in terms of global warming or just using power more efficiently, there's certainly reinforcement learning applied there. But in terms of general politics and all, I don't know, that might be a more human problem. But anything we can represent in this problem, in this formulation of environment and an agent which tries to maximize the reward, any goal can be specified. That was the hypothesis, the reward hypothesis. So you might be able to specify literally any goal. It's just how you set up the formulation and the agent and the environment.
Till now, is there any application of reinforcement learning in? Hi, hello. My name is Yash. So till now, is there any application of reinforcement learning in medical or healthcare?
Yeah, a lot actually. It doesn't mention it there. If it doesn't mention it here, this link here, the first link has a lot of applications in chemistry, in actual, obviously computer vision is very good at the medical side, but actually reading, what are they called again when doctors sign a report of the person's health and all the different, we can optimize that as well. There's many cases. So check the slides out here for more examples. Click the link of the meeting.
Hi, again. So you mentioned about actor-critic models, right? Mm-hmm. So even GANs are actor-critic models. So is there any code, is there any some sort of parallel, understanding of these two things? In a way.
There was a paper in 2016 which tried to unify the concept of Actor-Critic and GANs. GANs are two networks that train and fight against each other in order to generate better images. And Actor-Critic is kind of similar because we have a value network which tries to predict the value of the current state, and the actor itself which tries to, so there's a lot of analogs there. If I don't have a link here, but yeah, 2016 paper, and maybe David Bly had that. Yeah.
Hi. When you were talking about multi-agent collaborations,
say again?
Multi-agent collaborations, how are the agents communicating to each other?
So there's a few different ways to do that. There's a large field called multi-agent reinforcement learning, and there's hundreds of papers released a month on this now. You can have one policy which represents all the agents and can choose to do specific actions for the agents. You could do a hierarchical system. But DotA, shown here, what they did here is if there's 5 agents on a team, the 5 agents had their own individual reward functions, but there was one hyperparameter in the whole system which encouraged cooperation. So they cared about the other agents doing well. And they could set this hyperparameter to 0, to not care about what the other agents are doing on your team, or set it to 0.5, so you do care what the other agents are doing. That's one way, and I urge you to look into the field of multi-agent reinforcement learning.
Hi, first of all, thank you very much for the talk. I really enjoyed it. And apologies, you mentioned this earlier, but just curious, where could we find the work? And if somebody wanted to do work in a field like this, what would you recommend on how best to get into it?
Sure. So I'm going to share the slides on the Meetup page, and you can check our website, Medium, and Twitter for all our blogs, all our future blogs we're going to release. And then how to get into the field, study like hard. One thing I forgot to say was that I've been banging my head off a wall for 2-3 years now, trying to understand all the maths and the code and all the pitfalls that can happen when you try to code these algorithms. Things easily go wrong. I am recommending you to bang your head against the wall for 2-3 years, hopefully do a master's or do some course work and read survey papers and good tutorials. And actually, that's a good point. I have further reading here in these slides, so I urge you to check the slides. Further reading, more further reading, just general problems and future, as well as all the awesome videos, references, and yeah, so look at these for resources. Do I use reinforcement learning? Oh, the maths? What do you mean by use? You have to understand it, and then you have to put it in code. So you might spend 1 month just coding up the algorithm, but once you understand the maths, you don't have to look at it every day for that specific algorithm.
Right. Thanks for talking. I'm pretty informative. Question, because like a lot of the applications you showed, they are pretty cool, and a lot of the lists you showed up with possible applications are interesting. They are pretty innovative. But so you might think, okay, I can just maybe use reinforcement with can just use it to do whatever I want, to show apply to any kind of problems. Would you say there are problems that are not specifically good to apply reinforcement learning, or not really?
That's a very good point. I suppose when you have the labeled data, if you have 1 million cats and 1 million dogs, and you know the cats are cats and the dogs are dogs, that's a typical supervised learning problem. It would be kind of strange and maybe ill-advised to use reinforcement learning in that situation. Not everything can be, there is the reward hypothesis, but it is a hypothesis. Obviously, certain methods are better than others for specific problems.
So if you have something like, you just want to predict stock prices, would you use this or not?
Maybe not to predict the stock prices, but to make actions after seeing the stock prices. So you could have a portfolio agent that has 5 stocks and chooses to buy, sell at specific times depending on the stock prices, or even depending on the supervised predictions of future stock prices. Yeah, I can send you.
Just one question. So all these kind of approaches are kind of optimized, optimization to a problem, basically. Have you ever heard about Gregory Bateson and the double point theory? It's more coming from a communication theory problem. And the thing is, like, if you force a person into a situation where it only can lose, basically, it needs to find a different approach, which is basically breaking the rules. So, if I leave you 2 choices, like the Bretzel problem, and both are evil, and in both situations you will be left out worse. You don't want to choose between both kind of options. You actually want to break the rules and find a different approach. Is there any kind of approach in reinforcement learning to get into this kind of situation?
So in strict environments like games, it's a very controlled environment. These agents actually do sometimes hack the games and break the rules and find ways to actually, that the game designer never thought the game would actually break, but the agent finds a way. One example is Tetris. How do you win a Tetris when you're just about to fill up with blocks? The agent paused the game because that's maximizing reward. You don't want to lose. So that's one example. But in general, you only have the actions you're given and the states you can get into, and you can't really break the rules in most cases.
Just to go answering that question, I think a lot of things, a lot of the work sort of assumes that you have a very good model, and as you said in the game, it's a very good model, you know how the game works. You assume it's an exception. But in that situation that you're describing where there's two bad choices, well, effectively the problem is that your model, the situation isn't complete.
Yeah.
Because if there is a third choice that is going better or is much harder to find, that should still be available in the model, but it might get lost in an approximation somewhere along the way.
Yeah.
So a lot of this depends on general modeling principles.
Yeah.
That depends whether your approximation leaves these actions in, or it says, no, there's only two main options. There isn't a third one because it only comes up very rarely.
Yeah. So if there's two actions and there's only two actions, you should choose the lesser evil. But if there's never just two actions, and us humans, we have thousands of actions at our hands. So in a sense, ORL is very optimistic, and if we had a true general intelligence, it could do many sorts of things. It could think of 500 alternatives to Brexit.
Yeah, when it comes to applying RL in terms of automating machine learning, how do you optimize the reward? Because if you optimize the reward, it will turn up overfitting the data in the end. Yeah, so how do you balance that perspective?
How to avoid overfitting in ORL?
In terms of RL.
Yeah, that's a funny kind of joke, is that ORL is the only place it's acceptable to test or to train on the test environment. What we care about in ORL is actually just being able to solve the problem, and then of course you overfit. So what the Sonic environment here, OpenAI is finally trying to encourage people to do generalization, to test on levels that these agents have never seen. And obviously this is super popular in data science and supervised learning, but now we're moving towards there in reinforcement learning. It hasn't been the case for years, but now we're moving towards trying to train generalization into these agents.